Go
Hi,
ahead.
I'm Aarthi. I'm a freshman at the University of Chicago. This summer, I worked with Dr. Kyle Chard and Zihong on extracting scientific information from free text articles. So over 2.5 million publications are produced every year, and a researcher may have to read hundreds of publications just to have a rough idea of the current state-of-the-art technology in their field. And they still might miss key information included in those publications. And important facts are locked in text and thus inaccessible to computers. For this reason, we explored automatic and scalable methods to process vast collections of our research papers and to extract important facts from them, such as the properties of different polymers and compounds. Most prior work first applies a named entity tagger to identified named entities, but here we explore how we can develop a relation extraction model without using a named entity tagger. We do this for a couple of reasons. Named entity taggers require large, carefully labeled corpus to train on, which are usually non-existent for specialized domains such as polymers, and they only recognize entities that they are trained for, thus limiting the capabilities of otherwise totally generalizable pipelines. For our project, we used two different data sets pictured on the left, a noun data set consisting of 8,000 sentences, and on the other, another smaller polymer data set consisting of 114 sentences. Usually it's hard to generalize NLP models among different domains because language is domain specific. We wanted to show that our model was built from a baseline for extracting noun relations, and it can also be applicable to a data set from a completely different field. In the noun data set, we identified 10 different relationships that are possible between two different nouns in a sentence. One example of this relationship is cause and effect. In our polymer data set, we focused on 3 different relationships between polymers. One such relationship could be identified as one word being used as the full name of the polymer, and another as the polymer's acronym or label. For our models, we used a dependency parser provided by Spacey, which is a natural language processing toolkit, and customized it to fit our dataset needs. A dependency parser analyzes the grammatical structure of a sentence. We used a dependency parser because they're useful for extracting relationships between words using solely their parts of speech rather than their word type, as a named entity tagger would. Unlike named entity taggers, dependency parsers can be applied to text across different domains without any retraining. We did not use a named entity tagger as they're costly and take more time to run. Here in the center, you can see how we adapted Spacey's default NLP pipeline by removing the named entity tagger, abbreviated here as NER. So let's say our sentence is the one at the top here. After pushing the sentence to our model, the model correctly predicted that the pair of words would be configuration and elements. The model also correctly predicted the component-whole relationship between the words. The elements are a component to the whole configuration. The first way we customized our polymer relation extraction model was through tokenization. Tokenization is useful as it splits words or phrases into tokens, which allows the NLP model to better understand semantic relationships between words. And another method for customization we used for our model was training custom word embeddings. We use custom word embeddings for the model because this will allow the model to familiarity with the vocabulary in the data set. We used SIBO and skipgram to train our word embedding algorithms. So to scale our model, we used Parcel to create parallel programs composed of Python functions and ran our model with a larger data set on a set number of nodes and cores concurrently. It was easy to augment the current existing Python script and then deploy on Midway's RCC. And in this code snippet on the right, you can see that our Python app takes a string and outputs results in a text file. And on the left, you can see the configuration we used in our script. We were also able to check parcel logs for runtime. We evaluated our model based on general runtime on the CPU and GPU and performance over 15 epochs with SIBO training and skipgram training. We found that Spacey isn't optimized for GPU acceleration and that SIBO with default parameters outperformed skipgram. When scaling our model, we used a larger polymer data set consisting of 300,000 sentences from papers published in the Macromolecules Journal and retrained our word embeddings with SIBO default parameters. For single node scaling, we were able to reach a peak throughput of 103 sentences per second using 32 cores. And when scaling across 16 nodes, we were able to reach throughput of 590 sentences per second. So in conclusion, natural language processors for relation extraction commonly consist of 5 stages: tokenization, part of speech tagging, named entity recognition, phrase parsing, and information extraction. We were able to train and deploy a successful model without named entity recognition, and our model's best result for identifying polymer names and relations reaches an F1 score of 0.671, outperforming the 0.617 achieved by ChemData Extractor, state-of-the-art domain-specific toolkit available in the field of chemistry. And using Parcel allowed us to easily augment our existing Python script and deploy it onto RCC for results. Going forward, we hope that structured and scalable data extraction from publications will be able to process vast amount of data quickly. Thank you.
Cool. Does anyone have questions?
Yeah, I guess I'm curious. This looks really impressive, and it seems like this is enabling some nice things. I'm wondering if this is something that actually would be useful to a larger community, and if you have any ideas about sharing this with that community so that more people can do such research effectively.
Yeah, definitely. I would. The code is all open source on GitHub, so I could probably forward that to Kyle.
Okay. I mean, I guess the only thing I would say is that like making something available and getting people to use it can be a little bit different, and sometimes you might have to be more active in building a community.
Yeah.
Cool. Any other questions? We've got a couple of minutes left still.
I should say as
yeah, go on.
Am I unmuted? You can hear me?
I can hear you.
Yeah, I should say as well, Aarthi did all of this work in 10 weeks over the summer and also managed to write up a poster for the student research competition at supercomputing. And so this work will be presented there, where I think Aarthi's a finalist in that competition. So I just want to say this is amazing work for someone that hadn't yet started their undergraduate degree even. So that's all. I can't ask any questions because I know the work too well. But yeah, we certainly hope to continue using this. We have a PhD student that's working in this general space, and he's going to use this as a baseline for comparing against some of his neural network models, where we're applying it to materials and COVID publications to try and derive relationships between facts and papers. So yeah, just amazing work, Aarthi.
Thank you.